So today I would like to introduce you to the topic of quantization of neural networks. And to have a good understanding of what we'll be talking about, let's begin with the overview of today's presentation. First of all, I will explain the fundamentals of quantization, so the basic concepts, ideas behind this term. What is the purpose of quantization, and I will briefly describe the mathematical formulas behind it. Then we'll proceed to the main methods used for the quantization, namely post-training quantization and quantization-aware training. We'll discuss the pros and cons of both approaches and the differences between them. Knowing the theory, we'll proceed to the usage of the quantization methods with PyTorch, the most popular framework for training deep neural network nowadays. I will show you some snippets of code to let you know how the both post-training quantization and quantization-aware training is supported with PyTorch. Then I will briefly discuss the use case that we worked on a couple of weeks ago with Krzysztof Dziedzic. We worked on quantization of computer vision models, so it will be explained. And finally, there will be a slot for the questions. All right, so let's begin with the idea of quantization. This is the method of information compression, and I think it is the best to understand that by the example. So if someone asks you what time it is, usually you don't respond with the exact Unix time precise to the milliseconds, but you rather would say that it is 10:15. So you provide almost the same amount of information, but using much smaller number of digits, of words, smaller amount of data. And in the context of deep learning, quantization means reducing the numerical precision of a network's weights and activations from standard usual 32-bit floating numbers to just 8-bit integers. And it is shown on the graphics. On the left side, you can see the convolutional kernel with standard floating point weights, which can represent almost 4 billion numbers in the interval. And on the right side, you can see the quantized values. So the integer 8 values. This interval can represent only 256 different numbers, so much smaller range of possibilities. However, we'll see that the results obtained using both precisions are quite similar. So the benefits of using quantization methods are as follows. First of all, models get smaller because you don't have to save 32-bit numbers. Then the inference gets faster. Models are becoming available for mobile devices since most of mobiles work on ARM processor, which are suited for 8-bit data. There is a lower memory footprint and power consumption because of the size reduction. And with all the above advantages, the accuracy of the model should stay about the same. So let's proceed to some important terms. First of them is the mapping function, and it is the most important function actually, because it can quantize neural network weights and activations to 8-bit interval to a finite set of values. And the most popular approach for doing that is the uniform quantization, which results in quantized values uniformly spaced. Here we can see the formula for the mapping function. This is the rounded value of R divided by S minus Z, where R are real valued input of activation or weight, S is the real valued scaling factor, and Z is integer 0 point. We'll explain those parameters in a second. And on the graphics, you can see that the real valued weights, activations, are mapped to the 8-bit interval. So each value is going to be represented by the integer instead of the floating number. So let's move on to the quantization parameters, the scaling factor S and 0 point Z. The S is the ratio of the input range to the output range. and it is given by a following formula. This is a ratio of beta minus alpha, which is the clipping range of the input, and the quantization interval. So here we can just calculate it as a 2 power b, where b is quantization bit width minus 1. I see a question. Yes, there are other mapping functions because the quantization can be non-uniform. I don't remember exact formulas, but there are some alternatives. This one that I presented is the most popular one. Coming back to the presentation, the other parameter, z, ensures that a 0 in the input space maps to a 0 in the quantized space. Another important term is the calibration, and it's this process of choosing the input clipping range, so the alpha-beta interval. And the simplest technique for doing that is just to record the minimum and maximum values and assign them to alpha and beta. Another important term is observer. This is the module used for computing the quantization parameters based on layer statistics, either observed during calibration or during training, depending on what method we will use. Another difference between quantization methods is its granularity, as we can calculate the parameters for the layer's entire weight tensor or separately for each channel. The second approach, so-called per-channel quantization, is considered much better, and currently it is the standard method used for quantizing convolutional kernels, as the distribution of values for each channel can be quite different. All right, we have some theory behind us. Let's move on to the most popular methods, and we'll start with the post-training quantization. This is a bit simpler, as you quantize weights of already trained model. You don't perform any fine-tuning of the model. And quantization parameters are computed during the calibration process that I explained a couple of minutes ago. So on the schema, you can see how it works like. You take a pre-trained model and some calibration data. It can be just 100 or 200 samples, and perform some inference paths of the model. During this inference, the observers modules compute the statistics of distribution of each layer. And this is how we get this S parameter and Z parameter that I described. The main advantages of post-training quantization are that the overhead of this method is very low, often negligible. It requires very small amount of calibration data, and it performs very well in large models. By large models, we mean models with more than 10 million parameters. However, post-training quantization usually yields lower accuracies as compared to the second method, the quantization-aware training. The accuracy suffers in smaller models, and to stay robust against the drift in the distribution, we may need to perform regular recalibration. So moving on to the second approach, the quantization-aware training, the biggest difference is that we retrain the neural network with quantized parameters. The usual forward and backward passes of the model are performed in floating point, but the model parameters are quantized after each gradient update. I will explain it in more detail on the next slide. But as I said, the main difference is that you fine-tune the model, but with quantized parameters. So you once again take pre-trained model, bigger training data set, and perform fine-tuning. So the main advantages of this approach is that it yields better accuracies in comparison to post-training quantization. The quantization parameters are learned during training, so the accuracy is more fine-grained. And this approach is suitable for models with a long lifetime when we don't have to perform fine-tuning very often. On the disadvantage side, the computational cost of retraining the model is quite high. And in comparison to the standard training, the quantization-aware training should be performed with more epochs. So for several hundred epochs, it takes a long time, so the cost is really high. And as I promised, a couple of more words about quantization-aware training. There is a very important module, so-called fake quantization, which includes quantization error in the training class. And it works that way that we quantize the data and then dequantize it right away to get this quantization error and include it in the training class. The operations compute remains in float point precision, and in the forward pass, fake quantized weights and activations are used to perform the layers operation. And in the backward pass, we just update the floating point weights using usual weights gradients. All right, so that will be it for the theory. Now let's go to the practice. We'll focus on the PyTorch framework, which is supported, which supports quantization methods. First of all, we can select the strategy for quantization parameters with qconfig class. We can select observers, both for activation and for weights. Currently, per channel observers, so those better observers, are available only for weights. For activations, we need to use per tensor observers. And the available observers are minimum, maximum, moving average, and histogram. To see which one performs the best, you need to experiment with each other, but the experimentation process is quite fast because at least in case of post-training quantization, you don't have to perform any fine-tuning, just to quickly perform the calibration process. So in terms of post-training quantization, you need just 100 or 200 samples of representative data to calibrate the observers. And we can go through this snippet of code. First of all, you insert quant stub and dequant stub, which are responsible for correspondingly quantizing and dequantizing the data. Then we assign the config to the model. Here you have a default config, but you can create it as you wish. Then we use the torch quantization prepare method to just prepare the model for the calibration and perform some inference passes of the model. During this inference, the observers get updated, and we have correct quantization parameters, using which we can convert the model to the quantized version, so having 8-bit weights and activations. And in terms of quantization-aware training, as we said before, in the forward pass, quantization is simulated via fake quantized modules, which quantize and dequantize the data right away, adding quantization noise into the training class. And looking at the snippet of code, we just repeat very similar steps. So insert quant stub and dequant stub. We prepare our model, so assign config to it, and use different methods, the prepare quantization-aware training method of PyTorch, and then perform a standard training loop. And the difference is that this fake quantized module will be performed, and the quantization parameters will be updated. And finally, after the training is done, we can convert the model to the quantized version. So moving on, we'll discuss the use case that we were working on a couple of weeks ago for one of our clients. The problem was as follows. We got the baseline model, the non-quantized model. It was a computer vision one. The client used F2 score metric to measure the quality of the model, and he had 4 kinds of data sets to measure the quality. First of them was all data set that joined the remaining 3, which were split according to their difficulty. And the client, before we started working on the quantization, tried to quantize the model on his own and got pretty worse results. The downgrade was almost 3 percentage points in all data set and about 2.67 on easy data set. So we used both post-training quantization and quantization-aware training approaches. The post-training quantization methods performed better, surprisingly. We performed grid search for the best performing observers. And as a result, we got a model which was only 0.38 percentage point worse than the non-quantized version, which is really close. And on the easy data set, which was the main goal for the client, it was only 0.12 percentage point worse. So we got very similar model in terms of quality, but with the 8-bit weights. During the project, we found some issues with the quantization methods in PyTorch. First of all, there were some failings in quantization-aware training implementation, especially concerning the fake quantization module, as the quantization is still in beta version in PyTorch. So we were aware that it will not be perfect. The second finding was that despite the fact that fusing of modules is recommended by PyTorch in their tutorials, some of the already fused torch layers, like torch conv bn2d, so the layer that fuses convolutions with batch norms, don't work with the quantization methods, so they need to be separated, actually. And the last finding was that some layers, like transposed convolutions, are not supported with the quantization methods. So we needed to replace them with corresponding techniques. In this case, we used standard convolutions plus the upsampling layer. All right. Thank you all for the attention. I hope you liked it, and see you soon.